Here we have a car with a given mass is rounding a flat circular curve with a radius of 80 meters. We're given the coefficients of friction between the car's tires and the asphalt, and we want to find the maximum speed at which the car can negotiate this curve. So we imagine a circular curve. Here is our car traveling along that circular curve. It'll be traveling straight ahead at some unknown velocity, and the curve itself has a radius of 80 meters. So here the car is following a circular path. This curve is a portion of a circle. If an object is following a circular path, then by virtue of that, to stay on a circular path, there has to be a centripetal force acting towards the center of the circle to hold the object on that path. So what we're going to do is take a snapshot of the motion of the car. We're going to look at it from the rear so that we can see the centripetal force. So here's the roadway. Here are the tires of the car. And here's the actual car. Its velocity is traveling away from us. It's headed into the page because we're looking at it from the rear. We're looking for the forces acting on it because we know that from this perspective, the centripetal force must be acting to the right. So we'll use our standard process of identifying forces. We need to figure out what regular forces there are and see which of those forces are playing the role of centripetal force. So we draw a circle around the object. We look for points of contact. Here with the road, we have a normal force. We also have a weight of the car. And then in this situation, if the car were going straight ahead, there would be no friction. But in this case, we don't have a force acting sideways. And so we can surmise from that there must be a frictional force holding the car on the road, because if there were no friction, the car could travel straight ahead, but not turn to the side. Now that we've identified the forces, we'll go ahead and draw our free body diagram. Since our centripetal force is acting horizontally, we'll use horizontal axes. We'll represent the object, the car in this case, as a particle at the center of the free body diagram. And we'll draw our forces. We have weight pulling down, and we have normal force pushing up. There's no acceleration in the y direction, so those two should balance each other out. We have centripetal acceleration pointing towards the center of the circle. Our centripetal force has to point towards the center of the circle as well. And since there's no other forces that could play that role, that has to be our force of friction. And in this case, the car tires are all stationary relative to the road. And so this is going to be the force of static friction holding us on the road. If it were kinetic friction, that would mean that the tires would be skidding across the road. It would be in some sort of power slide, which is not what we're talking about here if we are negotiating the curve safely. We use the free body diagram to write out our Newton's second law equations, F equals ma, and we can break that up into components. Looking in the x direction, I've got my force of friction is equal to the mass of the car times the acceleration in the x direction. My acceleration in the x direction we see is non-zero. That is where the acceleration is in the x direction, but it's also not just any acceleration. It is specifically our centripetal acceleration. In the y direction, we have the normal force that points up. We have the weight that points down. And together, that is the mass times the acceleration in the y direction, and the y direction is zero. The car is moving across a horizontal surface, so there's no vertical acceleration here. The centripetal acceleration we do have an equation for. That is v squared over r, where v is the speed of the object going around the circle, the linear speed, and r is the radius of the circular path. Now, in this case, if we want to find the maximum speed, that means that we're looking for the maximum value of the velocity. If we have the maximum value of the velocity, that's going to correspond to the maximum possible value of static friction, allowing us to move at that speed. And so now we can take another step and we can simplify some of these terms in this equation. I can plug in with equations for maximum static friction and also for weight. From this equation here, I can figure out what the normal force is. And then I can plug this quantity in for normal force up there. I'm going to move this whole thing down here with the substitution. Notice how the masses cancel out. Even though we're given the mass of the car, oftentimes we don't need it and we can save some time by not using it. In this case, we're still looking for velocity. We know everything else. We have the coefficient of friction. Again, we want to use the static friction because the car tires are static relative to the road. They're not sliding. I can plug in for G, and I can plug in for the radius of the road, and I can solve for V squared, which is 667, and then I can square root that to find V, which I find as 25.82. Looking at my sig figs, I have 2 or 3 sig figs, so let's go ahead and say round to 3 sig figs here. I've got V equals 25.8. My units here should be meters per second. That should be the standard units in the metric system. We can go ahead and convert this 25 meters per second, and we can convert to kilometers per hour to give us a sense of scale. It's about 93 kilometers per hour, which is approximately 60 miles per hour, which, if this is a back road, that seems like that would be a good speed.